And now I really try to formulate the problems which I believe are solvable by people who more or less use modern theoretical physics. You may ask why I did not solve them if I did not get my prizes. Well, actually, I tried, and some things I did and something I failed. But there are also some new developments, and that would kind of bring hope. But on the other hand, from the viewpoint of a physicist, the most interesting part of all this turbulence as a highly fluctuating system is a symmetry. That symmetries we are talking are statistical symmetries, namely there are symmetries of the probability distribution, and some of them are broken and non-restored, and some of them emerging just appear out of like where they are unexpected. So today, the first part will be what I've already started last time, telling you about the broken symmetries. So namely, we were talking about the probability distribution of, let's say, velocity difference measured at a distance r, and we established before for purely engineering reasons that flow provides resistance in the limit of vanishing viscosity, and similar argument, we established the third moment of such distribution. And for quite different systems, compressible like Burgers, shock waves, incompressible like vortices, we established this more or less epsilon r. And we'll return to it. First of all, it tells us that the one important symmetry is broken is time reversibility, the existence of a third moment which changes sign upon time reversal already tells us that time reversibility is broken, which is okay. We understand it as an anomaly in which we provide dissipation even in the invested limit when friction goes to zero. But then we ask if there is some kind of self-similarity where this is 1/3. And that would be, of course, a huge simplification. That means that you don't need to measure function of two variables. If you are an experimentalist, it's enough to measure function of a single variable. And the answer was no. And if we ask what is the moments, how they actually scale, of course, dimensionally, this is all you can do. So whatever changes the scaling must come as a dimensionless number, and it's usually written, what stands here is a large scale, box size, forcing scale. So again, what we are talking is what is called on the jargon a direct cascade, because in a second hour today, we'll encounter inverse cascade, which goes from small scales to large, but this is now we have a big fun of a drive a car, we leave weight behind, so we create big vortices, and these vortices start to fragment and produce smaller and smaller vortices, and this is the scale of forcing. And what stands here, let me call it like this. Sometimes it's called dimensional anomalous dimensions, or in other terms, it behaves like some numbers, and these are not linear in n. And in particularly, what we found is that these zetas as a function of n for 3 that must be unity. For 0 that must be 0. And for, I don't know, some few decades, people believed that there must be a straight line. That would mean self-similarity of the distribution. And what was experimentally actually discovered was that it's some kind of a convex line passing through this, which tells us that these zetas, these deltas, n as a function of n changes sign it's 3. This is empirics. That's what we measure. And when I grew up, I didn't trust this measurement. I thought that they're just artifacts of insufficient resolution. Now we do trust. We have a lot of support. Moreover, we have this really simple case of Burger's equation, for which we have shock waves, where we have the same third moment, namely that it's here, but we know that for Burger's, it looks like a caricature of this, namely that moments with moments less than unity scale linearly, namely delta U proportional to R in the first power, it gives you this straight line. And here, the scaling does not depend on the moment because the contribution into these moments are given by shocks. So in this sense, this is now well established. But it's a very dramatic statement. If you look at here, it tells you the following thing, that if you keep a rate of your pumping, this is how much energy you pump per unit gram of your fluid, and you keep a given scale R where you measure, but your box size, your forcing scale goes to infinity, namely the number of steps of the cascade that you go from L to R increases, then moments lower than 3, including the second moment, which we discussed, go to 0. The turbulence intensity goes to 0 when the number of cascade steps increases. It carries the same flux. It dissipates the same amount of energy per unit time. It tells us the phenomenon which is sometimes called intermittency, including by the guy who worked next building for Karman. And it actually tells you that what turbulence looks like when this number is very large, when the cascade is very long, is a very rare, very strong fluctuations. Because the moments higher than 3, they go to infinity. It's a really very rare fluctuations which provide you for this flux, but the spectral density of turbulence, which is the second moment, goes to 0. So it's a very dramatic physical statement. And from the viewpoint of symmetry breaking, it's again anomaly, because this is, and that's why it's called anomalous scaling. In this called anomalous scaling exponent, because it tells you, of course, the pumping breaks scale invariance. The moment you have a car size, of course, it imposes a scale. But we would believe that at the very, very small scales, we forget. I mean, what was really driving? We would only remember how much we drive. The answer is no. So what I now want to tell you is a hypothetical way to solve this problem, at least not on a way what I tried to do last time, how to understand it. What are those numbers? For Burgers, we know that this number 1 comes from shocks. And incidentally, this is also true not only in a one-dimensional case. And at any dimensions, if you have a shock wave, right, then the shock front, and imagine that there is d minus 1 dimension in this. So if your interval of measurement r, this one, such that the shock is here, then it gives you contribution on the velocity difference, which is independent on r. But what depends on r is the probability to encounter a shock over here. And it scales with r linearly because the codimension of this front is 1. Namely, it's d minus 1 surface in d-dimensional space, or in one-dimensional space, it's just points where the fronts are. So now, when we look at this curve, it was always long an idea what would be maybe this is also saturates on some number which is related to some kind of a most singular object. And recently we've got experimental data which give hope. And this data, let me in a little bit exaggerated way. But first of all, this data is about so-called transverse structure function. Namely, we take 2 points separated by the distance r, and they have their own velocities, they're kind of different, but we project this velocity on the perpendicular direction. Okay? And we measure the difference of this. So we take delta v perpendicular, takes it in the moment n, and measure respective exponents. This is something for which we now have really good, like a couple of years ago, we have really good data up to 12. And this is somewhere 3, and this is 1, and this is 2. And so what we get is something which seems like it saturates to 2. And what it, yes?
Do we understand why this curves are always convex?
Yes, it's called Herder convexity, is something which follows from like Cauchy-Schwarz inequalities on moments. So it's kind of a simple property of when you average moments, there's always a convex curve, right? It could be not smooth, but it always convex. It cannot be concave. So what it?
I have a question. So
yeah,
a different correlate, right? It's transfer motion.
yeah, it's different.
So it's not obvious actually when going to have same exponents. For example, you said that
They are different. Absolutely right.
So that equals 3. Is it also 1 or not?
Yeah, it's n equals 3. It is also 1. There is some simple related to incompressibility way to relate one to another, and it's so kind of all third moments have the same exponent because they could be one recomputed way another, but at higher it's not. So at higher moment, geometry allows you for different exponents. Actually, the longitudinal are somewhere higher, which means that they are given by different flow configurations, less singular. The lower this number, this is zeta n, the lower this number, the higher the anomalous dimension, the stronger is your fluctuation, which determines this configuration. But what this 2 tells us? What it suggests? Suggests that you have something. So if it really saturates on 2, which means that the probability of this object is r squared. For Burgers, this unity means that the probability, let me make Burgers orange. So the probability of shock is proportional to x over L, where x is a distance at which you measure. Now it tells you that the probability of whatever the flow configuration you have, which determines these very high moments means main contribution is given by very strong fluctuations. What it means that it's quadratic? What's your
vortex?
It's a lie. Must be a lie. We don't know it's vortex or not vortex, but if you have linear object in 3-dimensional space and you take a given distance, then the area over here is the probability to have a line passing through it, right? So this is, and I remember that when I first seen it, I was really ecstatic. I thought this is a sign. And so now the question, what you can do about it as a theoretician. Can we compute this now? Okay. And of course, it would be nice to compute prefactor here. Prefactors definitely would be related to the force statistics. So now the question, how would you compute very high moment? Because we assume that the asymptotics at n going to infinity would be given by this line, and we expect it to be vortex line. So we now want to know how strong vortex lines could exist in the three-dimensional fluid.
Wait, for the longitudinal one, how big are these differently measured zetas?
20% difference, and I have no idea what gives longitudinal moment.
So they're higher than 2.
Well, first of all, no, they are higher, which means they are less singular. Okay, so they are closer to normal scaling. And again, it's only when you have saturation that you really start suspecting that there is a single flow configuration that give you all these moments. While this exponents start changing, it means the higher the moment, there is some mixture of different fluctuations which give you contribution into it. So only the saturation tells you that look for a single configuration. And how we may look for the single configuration or flow. Configuration means that the flow, something which and then create a very strong line. And this formalism, which allows us to do it, we call it instanton formalism for some, but it's something which relates to the saddle point configuration in the path integral. So what we need to do, we need to write the expression for this as a path integral over different flow trajectories. And say that for very large n, we expect that the main contribution into this integral is given by some very special, and that would be field, the field configuration, some kind of velocity or vorticity history. And that's when I want to tell you a little bit how one can do it. We actually did it for Burgers, for passive scalar, and for other things. And even we did it for Navier-Stokes equation in 2D. Nobody ever did it in 3D and found this, yes.
Is this data in 3D?
It's data in 3D.
Okay.
It's data in 3D, it's pretty recent. And in lecture notes, I give reference to it, so you can just look at this data.
One more question.
Yeah.
So this scenario where these lines asymptote to even one of them, either the transverse longitudinal transpose to something, means that the velocity field actually is not Lipschitz for any exponent.
Well, it's no Lipschitz the moment you look at third moment and see that it scales linearly, which means that it's at least Hölder 1/3. So Lipschitz will also.
Okay, fine. Yeah, when
This was Lipschitz.
Sorry, I forgot. I meant Hölder.
Yeah.
So that means though it's not Hölder.
What do you mean not
There's
Hölder?
no positive. Like for example, step like discontinuity. Like
Yes,
quantity.
it means that asymptotically we expect.
Like any constant would mean it's not Hölder.
Yeah, but on the other hand, what it means vortex line? It means that you have this vortex line, it rotates this, it's very strong. What it actually tells you that this vortex line, of course, it has a viscous scale over here, right? But when you measure velocity difference, it is this velocity, which this minus this is actually twice this velocity. It tells you that this velocity is actually independent on this distance because it's essentially a vortex line on a scale, on a viscous scale.
Like the worst.
But on the other hand, Burgers shock also has a scale which is a viscous scale.
No, that's also, it means that when you take the limit of zero viscosity, you end up with not just
this discontinuity.
Non-differential, but discontinuous.
Absolutely, yes. So this is discontinuity. Shock wave, of course, is also discontinuity in the limit of zero viscosity. But now it's a discontinuity not along the surface, but around the line, which means that your vorticity in this thing it kind of has a finite limit or goes to infinity when viscosity goes to zero. Okay, good. So how one goes about it, and I think that probably you are this way somehow deal with such things and all, but there are a few peculiarities which I want to stress. First of all, we are now very much in the domain of theoretical physics and not engineering, which means that now we really try to simplify problem as much as possible. Okay, And so, let's say you have a general equation for which is Navier-Stokes and Burgers. And what you want to do, you want to derive it by external force. Because really, in a flow, we do not impose statistics. All these instabilities which develops, they impose statistics. But now we say, okay, let's have it under control. So we assume that we have some external force, and we'll average everything over the statistics of this force, and this force will be Gaussian. This is the first simplifying assumption, which means that if it's Gaussian, it's completely determined by its mean value, which is 0, and we also say that we defined its variance, and we take it wide in time. It's a strong simplification, but it's physically completely legitimate. There is nothing wrong with considering such a force, which is, and we can even do it experimentally if necessary. And there is some pair correlation function, psi of r. I already mentioned it in the previous time. So what we assume that this psi of r as a function, well, it's something which, if we deal with Burgers, this is just a scalar function. If we deal with Navier-Stokes, this would be a vector, and this vector will be divergence free because we want incompressibility. I just kind of put it all understood. So it's something like this, and we assume that this is our correlation scale of the force. That's the assumption. Now, whatever we do, we need to average over the statistics of this force. So, for example, if I consider u in the power m, or any functional of u, if you wish, let's say just any f of u, I want to average. How would I need to do it? If I write it as a path integral, I would say that I average over all possible u as a function of r and t. I would be solving the equation, and I need to average over all possible forces with I write it very symbolically, with the statistics of this force, okay? Which is Gaussian. That means that the exponent minus f dot squared with this chi as a pair correlation function. Of course, as a standard trick, which you've seen many times, I can write this delta function as an integral of some extra field of the exponent. Because when you want to do saddle point, and of course this you need to put f somewhere here. So now, what you do, you write it as an integral du. You introduce another field p, which is also a function of r and t. You write exponent of integral over dt I p, and here is ut plus l minus f and p of f. Okay, and you also need to integrate over dn. Now, what you can do in this integral is that you can, and that's why we assume f to be simple Gaussian, you can compute this Gaussian integral because it's just an exponent of f, which means that if you do Gaussian average, so what you get? You will get now integral over du, integral over dp, you f of u, and you will have exponent, let me write it like this, which is some action. And now I'll write the expression for it. My action is I integral dt integral dr of y of r in t, my equation of motion, plus L of u minus 1/2, and of course that's exponent of f would give me, after Gaussian integration over f, the expression, it is p times f. So after integrate over f, it will be quadratic in p. It will be single integral over time, but it will be double integral over distances. It will be chi r minus r prime, p of r, t prime, p of r prime, t prime. So that's a kind of a standard, it's kind of warming up. So we wrote, and of course there is f of u here. So what you can also do, you can also put it over here. In particular, if you compute something which would be u in the power n, which means that what would stand here is n logarithm u. And of course, this means that it's measured at some time t, at some r equal to 0, at some time 0, r equal to 0. So now, if your quantities that you average contain a large parameter n, then you may hope it's not like you do, for example, in quantum mechanics, where your large factor stands in front of your action. It's not. It's only one term in your exponent, which is as a large parameter n. So it's not guaranteed from the beginning that when this parameter n goes to infinity, then the main contribution into this past integral du dp would be given by a single or by a family of configurations. Okay? And again, I don't have a very good classification when it does and when it doesn't. Several cases it happened to be so, in other cases it was not so, and I'm not sure that I understand clear difference. But what now I assume it, so namely I assume that when n goes to infinity, I need to take this action, vary it with respect to p, then I will get an equation ut plus n of u equal to minus integral chi. So when I vary, do variation with respect to the field p, so this would give me this equation, and the variation of this would give me integral of my force correlation function with my field p. Okay? Again, if you all seen it, I can go faster, or it's okay. I mean, how slow am I now?
That's fine.
Okay, good. So if you feel that like I'm telling something that you've seen many times, so it's chi r minus r prime, p of r prime, t prime, dr prime, dt prime. So what it tells us that you need to solve your equation, whatever it's Navier-Stokes equation or Burger's or whatever. There is, yeah, wait, yeah, when I vary with this, no, there is no, it's just T, G, R, right? Okay, this is R. And you will have a second equation because now you need to solve it with an external force which is dependent on P, which actually response function. If you compute, for example, UP, it's just your green function, your response function with respect to infinitesimal force. Or this is a variation of your U with respect to force F. So when you vary with respect to U, so you get minus PT. From here, you get plus P dl du. And from here, for example, if that was your u in the power n, you would get delta function of t n divided by u times 0. Okay, so those what we call instanton equations, and sometimes it's called optimal fluctuation method. There are many names for it. For some reason, I don't know, purely historic. We call it instanton because it's something which appears out of nowhere, which is in a moment will be clear, because we now ask what are the boundary conditions to this equation. Okay, so first of all, I need to my measurement. I mean, let's say this u. I say that this was u measured at time 0 at point 0 times in the n, which means that my p of t identically equal to 0 when t is larger than 0. So if your p is larger than 0, that's just by integrating this over time, you obtain a condition p at t equal minus 0, just given by this. Whatever you measure actually determines the condition on your field p. In this particular case, it will be u. And you need to impose condition on u again from extremum that u goes to 0 when t goes to minus infinity. So essentially, physically, what type of the problem one need to solve is that you assume that at a very distant path, you had what is you may call vacuum. So there was just 0, and then an external force appeared and started to grow UU forward in time, and then its own, not what stands here, for example, if it's Burger's, then your L is UUX plus nu UL minus nu UXX, right? And somehow nonlinear dynamic happened and they determined it. But what is this force? It's actually something which is determined by P. So, and what is here important is that when you look at this equation, for example, for Burger's, it will tell you that minus PT plus UU plus UPX minus mu PXX equal to 0. And let me remind you that for U, Burger's has this form, which tells you that your problem for U is well posed forward in time, because viscosity acts forward in time as a diffusion. But for P, it's opposite. Sorry, yeah, like this. It's opposite. Namely, for P, your problem is well posed backward in time because your diffusion has an opposite sign. Because you do here variation, right? And indeed, for P, your condition is at the end of your evolution. So you need to solve a problem for P backwards in time and problem for U forward. It's like a shuffle. We actually developed back 20 years ago kind of a numerical algorithm which does like this, which starts from like trivial, again, as with any iteration, you need a smart guess what type of solution you look for, but then you solve forward in time U's and backward in time P's and forward in time and backward time, and you hope that this procedure would converge. Somehow, if you try to do it analytically, which we managed to do for passive scalar and for Burger's, it took surprisingly a long time, even though for Burger's it's a one-dimensional problem, and you know what should be. It just should be a shock. What you really try to do, you try to find out what would be the amplitude of the shock as you start to grow it from the distant path. But that's essentially the lesson. So if we want to describe this, what I think one needs to do is, let me go with it. I think that the best thing is, and kind of most symmetric, is to consider vorticity, which is the kernel of velocity, and then look for omega, let's say, the component in the power n. Okay, so you need to write now what form your operator in this case take. If you take Navier-Stokes equation and you take a curl of it, you remember that we have And so if you take curl of this equation, what you get is the equation that d omega dt, and curl of it would be 0, but you would get on the right hand side is omega at v and plus viscous torque. Of course, this d omega dt is d dt plus v graph, is the usual thing. So when you now try to do this type of instantal equations for vorticity, what we will be essentially solving, let's say some point, for d omega dz dt, it would be omega z dvz dz plus integral of some kind of forcing. And then you need to solve equation for dp dt, for dp dt with these things. And physics is more or less understood. So what you would have here, you would have must have a stretching. So you start from omega at a distant path which is 0, and you want to understand what kind of a strong vortex line you can get, which give you this this scaling, which is proportional to the line, and you also want to compute the magnitude of it. So you need to start from omega 0, and initially you would have this additive forcing, which would be due to this p evolution, and then eventually you have nonlinearity. This is a nonlinear force. The velocity field that you create would stretch this vortex line, and the stretching, which is the problem is that you need to solve it globally, and it's very easy to find out, for example, linear profile like v z equal to lambda z. That would give you stretching, etc. And this lambda could be even function of time. The problem is that its energy is infinite. So if you try to compute action, it would be infinite. And so you will have zero probability of such things. So somehow this forcing, where is my, which has this finite scale, must really determine you, because what we compute anomalous contribution. This anomalous contribution, as you see the A over there. So we try to compute this, but this is an account of the forcing scale. So the solution which we'll find, it's something which must be described on the scale of forcing. So in a sense, kind of it boils down to the following thing. There are two partial differential equations, nonlinear, but that's it. So you reduce your field theoretical problem to the problem of solving two differential equations. In principle, they could be solved on computers, but this is not trivial, because for this you really need a very good guess. Again, because this is well post forward in time, and this is well post backward in time. So if you want to do this shuttle technology, you need a really good guess for your iteration, or you can try to show analytically that this equation have a solution which eventually grow a vertical line which produces contribution of the moment that is dominant. So this is essentially the problem. Maybe in the second half of I'll tell you how we did it for 2D, and it was very different from 3D. But at this point, I want to finish it because I now want to go into two-dimensional turbulence. So questions? Are you ready to start solving this problem? Or there are some?
You made a comment earlier about how this is related to the statistical symmetries in the problem. Can you tell us how that's visible from these equations?
What I'm now trying to deal, I'm trying to show breakdown of scale invariance. So to show the breakdown of scale invariance, and it's breakdown in the statistical distribution. What I'm gonna show you the fluctuation which is so strong that it gives the main contribution in moments, and this contribution explicitly contains large-scale forcing scale. That would be explicit demonstration, and then we did it for Burgers. So for Burgers, you can do it, right? Just can show how your forcing scale gets translated into a moment at however small scales compute. So now what we want to do three-dimensional analog of it. Show something which tells you that no matter how small scales you look, you will have contribution of your large scale forcing scale, and that breaks scale invariance. Okay? So look, eventually we aren't engineers, right? So we don't try to compute something which determines, how many trillions of dollars we burn through pipes. That's a different problem. That's what we already talked, and I'll finish with it next week. But now we really try to establish a very remarkable fact. And this remarkable fact are those deltas, anomalous exponent. But they bring L into the problem. And this is a way to show how it actually, just to give a demonstration. Okay? Okay? Yes?
But why is it L and not any other length scale? Some microscopic length scale?
Well, first of all, it's a very good question in the sense that we may ask, we break scale invariance on both ends, right? So we have a large scale forcing and a small scale dissipation. Okay, and it's not that exactly trivial to show that if you consider velocity difference at a given scale, then it survives turning visco scale into zero. So at some we forget about UV cutoff, but we always remember infrared. Okay. That's not it, but that's a separate problem. This is something which actually mathematicians are now pretty well are doing. It's something which tells you that as your viscosity goes to zero, you still have this anomaly, which is breakdown of time reversibility. Your velocity field is getting non-smooth. But this non-smoothness is not in incompressible case, not of the type like you depend on the scale. Okay, so this is like two different things. This is something about infrared. This is a way to show that your infrared always there. Okay, so we go down in dimension, and then things getting really beautiful and much better, but no less complicated from the viewpoint of a theoretician. So now now we'll have emerging symmetries, and this is much more beautiful, I think, but it's not no less difficult. So 2D, what will happen in 2D is that V is two-dimensional, then omega has vorticity, has only Z component, right? And then this scalar product is zero, right? Because there is no VZ, right? There is only. So what we have in 2D is that you can write Euler equation, invisible equation, in a very simple form. When there are no forcing, no viscosity, it's a very beautiful symmetry. It actually tells you that every fluid trajectory keeps its vorticity. So whatever vorticity you created initially, if there is no viscosity, it just gets transported. Okay. In particular, it means that the integral of a space of whatever function of omega is just integral of omega. In particularly, if you consider omega squared. This is called entropy for some reasons. Now we also have an integral of motion, which is v squared, which is a kinetic energy. And the existence of two quadratic invariants means very dramatic thing. So if we imagine that in K space, we somewhere have K on which we produce input. So our forcing, like what we consider in this case, so our forcing, this chi, which existed on a scale L, so let's call K 2 pi over L. So I assume that at this scale I have an input of energy, which is epsilon. Then I also have an input of entropy, which is K squared epsilon. This is my inputs. Now I want to imagine how would I create turbulence. And turbulence means far from equilibrium, and far from equilibrium means that your scale of excitation is very different from your scale of dissipation. That's the definition. This ratio of scale is your degree of non-equilibrium. In equilibrium, we have fluctuation dissipation theorem, which tells you that at every K, you put your thermostat puts into the system as much as it dissipates. Non-equilibrium means that you detached excitation scale from dissipation scale. This is what is Reynolds number, if you think about it for fluids. So now, if we assume that there is somewhere K2 and there is somewhere K1, so what I would have, let's say, here dissipated epsilon 1 and here dissipated epsilon 2. So I need to require that epsilon 1 plus epsilon 2 equal to epsilon. That's my energy conservation. If you wish, now I'm doing a really very simple linear algebra. And also I need to require that K1 squared epsilon 1 plus K2 squared epsilon 2 equal to K squared epsilon. Right? There's two equations. So from here, I may say that epsilon 1 is epsilon minus epsilon 2. But if I plug here K1 squared, epsilon minus epsilon 2 plus K2 squared epsilon 2 equal to K squared epsilon, I find out that epsilon 2 from here, K2 squared minus K1 squared equal to epsilon K squared minus K1 squared. Okay, so my epsilon 2 is epsilon K squared minus K1 squared, K2 squared minus K1 squared. Okay. And similarly, you can derive epsilon 1, which is epsilon minus epsilon 2, which is equal to epsilon K squared minus K1 minus K squared, K2 squared minus K1 squared. Now, what it immediately tells you, the necessity of the, say, of two cascades. First of all, you cannot satisfy this two relation without two dissipation region. And second, it immediately tells you what happens, for example, if your K1 goes to 0. If your K1 is much less than K, of course, it's also less than K2, right? It means that you can forget K1 over here. And what you find out that in this limit, your K2 squared epsilon 2 equal, approximately equal to epsilon K squared, which tells you that all the vorticity which is produced here is absorbed here. Okay? And it's a direct cascade. Again, terminology towards large K is called direct, towards small k is called inverse. But now, if you look in here and you assume that K2 go to infinity, not K1 to 0, but when K2 go to infinity, then your epsilon 1 is approximately equal to epsilon. namely all the energy is absorbed here. And of course, in the limit, when this goes to zero and this goes to infinity, you have two cascades where all of your energy is absorbed here and all of your vorticity is absorbed here. Okay? And inverse cascade is really a very strange thing, if you think about it. How it's manifested physically. So you do some small scale steering in almost planar flow, and larger vortices start to appear. It's a way of self-organization. And Anzanger was first who kind of had a feeling that it must be like this, but then again, you can look at nature and you can actually see it. You can see how out of small scale turbulence, and also we now know that big hurricanes are also fed by the small scale fluctuation, which can get the energy into large scale flow. Okay. So now what we talk about is about this two-dimensional turbulence, and it's very interesting, right?
Just to repeat, so unlike in 3D, saying in 2 dimensions, dissipation, this anomaly. So here state actually is at large.
Let's talk first of all about dissipation, because now what we know that if your, let's look here, if your K2 goes to infinity, it's essentially in viscid limit. It's nu going to zero. Your K2 is your viscous scale, right? What it tells you? It tells you that all energy goes towards large scale. There is no energy dissipation in the viscid limit at viscosity. It either creates a big vortex like a Jupiter red spot, or what we call condensate, which mainly in the box where we do experiments, we just see this big vortex appears, and eventually just wall friction which stops it. Okay, so there is no energy anomaly in 2D.
The driving force is usually applied at large scale.
Driving force is applied at some scale. If you apply your steering at large scales, then in 2D, when viscosity goes to zero, you would have your amplitude of your flow that you grow to infinity.
If I apply large scales of
Imagine that you are in a box and you have fun, just, you have, I mean, what we do experimentally, we take a thin layer of a fluid, we put magnet below it, and we run current through it. So we have Lorentz force, we just create a vortex. Or we can create many vortices if we took small magnets. So in this case, you ask, what happened when you decrease viscosity? If you have a steady state, which means that as much as you put into your flow, it is as much dissipated. But as opposite to the three-dimensional case, where the velocity magnitude saturates, and what increases with viscosity going to zero is the velocity gradients, what happened in 2D, that velocity magnitude would grow. So limit of zero viscosity or vanishing viscosity would not correspond to non-smooth velocity. It would correspond to very large velocity, so that even on this gradient, this small viscosity can produce you the dissipation. It squares very nicely with mathematical theorems, which tells you that if you remember at the very first lecture, I mentioned this millennial problem. If you start from a smooth flow, could it get non-smooth? In 3D, this is a problem. In 2D, it's proved that it remains smooth forever. Namely, you cannot create non-smoothness out of it. So there is no energy dissipation anomaly. But then you may ask, what about entropy dissipation? What happens, because what we are actually saying here, that if you have a steady state and your K1 goes to zero, that all, so there is no K1, that all your vorticity, here it is. Where it is? Yeah. So all your vorticity squared must be dissipated over there. So what really in this case exists is that you viscosity goes to 0, but the rate of omega squared dissipation stays fine. Not of energy, of curl of energy squared, of curl of velocity squared. And so maybe at this point I'll make a break, and then we'll continue after the break. Okay. Okay. So let's first do simple things like we did it for anyway. In new turbulence, we start from defining what is the flux. So as we discussed in this direction, this omega squared must flow, and in the opposite direction, energy must flow. And you remember how we did it? For example, for Burgers, we just considered ddt of u1, u2, and we got something like u1 grad u1 grad 1 u2 squared and u2 grad 2 u1 squared, and then we say that 2 is minus 1, and then we presented it as a part of u1 minus u2 cube, and it was dx1, and there was forcing here, and fu gave us epsilon. I just schematically remind how we obtain the statement that the third moment, delta u cube, became like epsilon x, 1, 2. So now what we need to do similar things in these two cases, but one would be about omega squared and another about v. So if we do just the same thing for omega, that essentially the relation that will be considered would be like this. And let me call it P2. P2 is a ddt of omega squared into omega by force. So it's an input rate of omega squared. So now if we look at if there would be v here, when we get the same for velocity, v1, v2, we get this statement that cube velocity difference is linearly proportional to the distance. That gave us this 1/3 scaling, which some people probably will not get Phil's medal for proving it. But now we have omegas here, and omegas is a curl of velocity. So if you just do power counting, what stands here, the left hand side, is essentially v cube divided by r cube. So kind of just naively power counting, we would say that v is proportional not to r 1/3, but to r. Well, that would be a smooth flow. What if delta v proportional to r?
So we're just get R cube.
What I'm saying is I'm just do power. Look, this is a constant. This is my dissipation rate. When I did it for velocity, there's this v here, right? So what I've got v cube divided by r epsilon. R, 1 over r comes from this gradient. Okay. Now I have two omegas, but omega is v over r by scaling, right? Because it's a gradient of v. So this left side is v cube over r cube. Okay. So it tells us that whatever this direct cascade happens, of course, it cannot be smooth because, as we discussed, when viscosity goes to 0, it must, when K2 goes to infinity, it must still provide for a finite dissipation. But what it follows from this power counting, that this non-smoothness could be only logarithmic. There could not be a power law non-smoothness like for velocity inverse, like for energy cascade. So this is a very kind of hand-waving argument, right? And so essentially what it suggests that if you look at correlation functions of vorticity, they must be somehow logarithmic. But you can also argue it from the way I did, and I did it kind of too fast. So now let me
So the dissipation is dissipation of sense strictly.
dissipation of omega squared.
Yeah.
Okay. So now let me give this argument a little bit similarly to the way I argue about passive scalar. So now I am in 2D. So my equation is d omega dt. That would be 0 if I would have no forcing. If I have some forcing, let's say it's phi. So I might present my omega 1, omega 2 correlation function in the following form. I need to take every omega and write it as an integral from minus infinity up to time t of my phi integrated along a trajectory which comes eventually, so my r at time t is equal to r1. Okay? We did it for passive scalar, but this is essentially omega is like a marker. Omega is conserved without forcing, and at every point is just integral of forcing from backward time. The same here. So what I will get if my this force is also Gaussian force with a pair correlation function determined by, I always will call it pi of r delta function of t. So what would stand here for this pair correlation function is an integral over dt prime from minus infinity to time t, where I measure if pi of r1, 2 as a function of t prime, dt prime. So what I need to do essentially is to take two trajectories, which at time, this is my point 1, this is my point 2. And I need to integrate them backward in time and see how much omega they get from their forcing, which grew them up. But my forcing is a direct cascade. So again, my chi as a function of r, something which disappears when distance is larger than L. So what well, this is twice time. So what I essentially would say is that this integral is chi of 0 could be estimated as this, which is exactly P2. Because phi times omega is P2 times typical time that it takes to get from R12 to L. This is a very, very general argument, which tells you that if you are interested in the pair correlation function of a Lagrangian invariant of a tracer, you just need to integrate correlation function of the forcing, or it will be multi-point correlation function if you correlate multi-point, backward in time. Now, if your velocity is smooth, namely, your delta V is proportional to R, the distance, which means that your dr dt, where this is at a given r of t prime, as something which is like lambda r, that's what we get in the dynamical chaos and all this smooth dynamical system with just exponential stretching. It will tell you that r of t is r of 0 exponent lambda t. It's intimately related to the exponential stretching means it's smooth. It also means that it's Lipschitz. Delta V is Lipschitz. It means that when r of 0 goes to 0, this is also goes to 0, not like for Richardson diffusion. We discussed it in the very first lecture. But then what it tells you that the time that it takes to get from R12 to L, this time is of course logarithmic. And so you would say that this is P2 over lambda logarithm L over R1, 2. And that's kind of zeroth level of consideration of this direct cascade. But then you say, wait, but what is lambda by stretching rate? It depends on scale, because as I go, like for Richardson diffusion, as I come to larger and larger scales, there are larger and larger vortices which participate. Here it's smooth, but it's not exactly smooth, it's almost smooth. So if you naively estimate this as an omega perspective, so you would get something from this relation that your omega behaves like p log the power of 1/3. So this correlation function would be logarithm in the power 2/3. This is a plausible assumption. This is what is in the end of lecture notes is listed as the first problem of turbulence theory, is to prove this 1/3 scaling, but it's 1/3 in logarithm. Okay.
It's 1/3 power.
It's a hand waving of, if I would have a stretching rate which is constant, then this stretching rate, then my omega 1, omega 2 would be P2 over lambda logarithm L over R. Okay? But it's actually not, because what it tells me that my field is not exactly smooth. It has this logarithmic non-smoothness. This actually, mathematics allows you logarithmic non-smoothness for this flow. And so the argument was that this lambda is by itself, you can treat it as omega at a given scale R. This is very, very... Okay, I mean, this was qualitative idea of Kreitman, and then we did this kind of hand waving. I don't consider this problem solved. The answer seemed to be correct. So people even see that omega 1, omega 2 is the logarithm 2/3. After much things, they even kind of, you may try to do it similarly to instanton. So you can say, okay, could I compute it for very high power? For example, something like omega coarse grained on scale L in the power n. This is now something which is a very different problem from 3D, because the equation has no stretching of vorticity. So vorticity by itself, I just transported, it could be only, but then again, with some kind of level of hand waving, and I really don't want to go there. I just want to give you a feeling what kind of problem one needs to consider when you consider direct cascade. And I don't want to spend much time on it, because now I want to show you in the remaining half an hour a real miracle, which I believe is a much more interesting problem from the viewpoint of field theory, and this is something which is related to inverse cascade. Okay, so if there are some questions about direct cascade, I understand that I presented it very briefly. You can look into lecture notes, but I really don't want to spend more time on it. But if something totally not clear, I'm ready to answer. Okay. Inverse. So what I will now show you something pretty strange. When we look at the inverse cascade, it's still the energy cascade, right? Which means that the same statement, delta U is epsilon R, 3/2. You can even compute the coefficient. You can check higher moments. With very high probability, with very high accuracy, it's n over 3. It seems that the statistics is scale invariant. Nobody ever proved it theoretically. In lecture notes, I list few maybe possible direction, but I must admit I tried them and I failed to do real proof. Physically, it seems natural. You have a small scale forcing. You consider something now at really large scales. And also, if you look at this scaling, delta V like R1/3, and you ask how time scales with the distance, which is R by delta V, it's R2/3. Which means that the larger is that your vortex, the slower it goes. So if you're interested in statistics at large scales, it's something which must self-average over the small scale fluctuation, which is opposite to the direct cascade where you have this large scale forcing and you consider something at a very small scales inside the forcing correlation scale. Still, nobody proved this relation. This is an empirical statement. But the moment you see scale invariance, you get greedy and you start asking, can it be promoted to conformal invariant, to something which is locally scalable, namely global scale invariance means that you can take your box, you just can expand it, and or you can look at a given region and just contract it, and it would be locally have the same statistics. But conformal invariance is much richer. It tells that you can here locally contract, here you can expand, but if you go in a smooth way, preserving angles, and do this transformation of the whole domain, your statistics will be, you can map your statistics in the undistorted domain into the statistics in the distorted domain. And so Polyakov wrote it some at 90s, this hypothesis that the turbulence in 2D must be conformal invariant. And I immediately, and it was kind of silence, like turbulent people did not know what to do with this statement. And then I wrote a reply that it's impossible that we have third moment. At the third moment, there was kind of arguments which were essentially not a mathematical type argument. And then another 15 years later, we actually discovered this conformal invariance in a very particular form in a very interesting object. And this object, now where I want to spend the rest of time is to introduce this new mathematical object and tell you how it actually relates to turbulence. And the object is called SLE. I don't know, somebody heard about it, you've heard lectures about it. Okay, so let me try to be slow and more or less eliminate it. It all started from A, which is Lewner, was Carl, and then was Turner himself when he ran from Germany to America, turns into Charles. So what Lewner invented is a very interesting way to encode a curve in a plane. So imagine you have a half plane, upper half plane, and you have a curve which goes from the boundary. So what you can do, you can consider this curve as a part of a boundary and map it by Riemann theorem into just half plane. So what you do a map, let's call it G, which maps half plane minus your curve. I will curve my curve gamma into just half plane. Okay? So you consider it as a slit, you kind of absorb this slit into your straight boundary, right? So the tip would go somewhere, will be part of the boundary. Okay? Now what Lewner suggested is what is called Lewner evolution. So already 100 years, mathematician really kind of, it's a very powerful tool. He said, assume that this curve continues. So I would present it as a function of a parameter t, which is my internal coordinate. It's not time from my dynamical equation, just internal coordinate along the line. And so this function g will be also dependent on t. And so this position, let me call it psi, will be also a function of t. So what Lewner suggests, and I personally find it very appealing because I am a random walk guy, and so for me it's very natural to look at something which just moves. So what he says is that any form of a curve in a plane can be encoded in this law of a point on a straight line. That was called Loebner revolution. It's a very powerful mathematical, simple and powerful mathematical idea, and it's encountered, it's encoded in a very beautiful way, because what you need to assume, I can just use my notations correctly. So, of course, this curve is finite, which means that very far away over here, you assume that your G as a function of Z, your map, is asymptotically Z, it's close to identity. And the expansion starts from 2t over Z, I mean, the next terms. So the t, this is actually normalization of this internal coordinate over here. It could be done through the asymptotics of G here. And then the equation is very simple. It tells you that dg dt is 1 g minus. Okay, so with 2. So this is called Loebner equation. It's unbelievably simple and beautiful. Every time you give this, you solve this, and it essentially gives you the map which absorbs your curve into the ground. Okay, that was 100 something years ago, 20, yeah, 100 years ago, and then Adele Schramm, who we actually came at the same time, Weizmann, or young assistant professors. And I remember I tried to get him interested in turbulence, and he said, I mean, look, I can do only Brownian work. So what Adele said, he said that if this is a Brownian work, then this is conformal map. In what sense? In literally in the sense, so if you have statistics of the curve in some domain, you can map it into any other two-dimensional domain, and any statistics of given point would be mapped into the respective images. But when it's a Brownian work, it's characterized by its kappa. And now kappa is dimensionless, right? So this is just a number. And all the fun started when people started to identify different kappas with different classes of curves in statistical physics. For example, you take Ising model, and in Ising model on a lattice, you can have a domain wall which somehow behave the boundary between spins up and down. Okay, it's a random curve at criticality. You may ask if in the continuous limit it would go into the curve of SLE class. The answer is yes. Kappa is equal to 3 for domain wall in Ising model. Then you can have even simpler universality class of critical phenomena, and this is called percolation. So let me say a few words about percolation. So let's tell me. You can think on percolation in different ways. One of the things you can consider a landscape H, which is a function of x and y, kind of some surface. And it has kind of a deep valleys, and it has some mountains, etc. And you started filling this landscape with water, right? And you assume, of course, that this is a random function, so its average value is 0. And then when you start filling your water up to level 0, you say that there is some critical level at which it's the same probability as to run by Earth or to swim by water. And this is the critical point. And then you this shoreline, when you in XY plane, you ask what is this line, right? Another way to, and but generally you say, okay, it depends on the statistical properties of this function h. Okay? And in particular, let's imagine that this is a Gaussian function. So this again is characterized by its pair correlation function, 0 is 0. You would expect that it's something which x squared plus y squared in some power a. So then what is known that if this a is larger than some number, which is 3/4, then everything which is a has larger is as if it is just short correlated field. Namely, that the correlation decay fast enough so that all the cases with a larger than 3/4 belong to the same universality class. This line in the limit has a fractal, it's a fractal. It has a fractal dimension, I guess, 7/4. And of course, then you run to Schramm and his people, and they say then kappa equal to 6. Okay. And you can also look at it from a lattice viewpoint. For example, you can have a boundary, and you can have a hexagon on this boundary. Well, I'm very bad in drawing hexagons. And so if you start here, they're all black, and here is you hit hexagons, and with probability 1, you can color it black or white. If it's white, you turn right. If it's black, you turn left. And this is the latest model from which you, in the limit, build a short correlated landscape, and the isoline on this short correlated landscape, it's getting so. First of all, we see that now the different kappas they correspond to different classes of randomness. In the simplest case, when kappa equal to 0, then it's just a straight line. You just look here, this is just a constant, so you have a straight line. The larger kappa gets, the more wiggles and more random this curve. So in this sense, kappa equal to 6 is a more random curve than, and there are many beautiful mathematical statements made about such curves, which can be directly translated into the language of a respective field theory, which corresponds to the criticality of percolation model or Ising model or any other things. And first of all is a very special property of kappa equal to 4. And it was proved that if your kappa equal to 4, if your kappa is less than 4, it's a simple curve. Simple curve means that it never touches back to itself. Okay? If it's kappa larger than 4, then it's not a simple curve. And then, let me draw it here. So if you have a curve and it somehow returns to itself and then goes and then returns to itself, because there are like double points over here. But then you can look at it and define an envelope, or they call hull. You can define a curve which is visible from infinity. If you look from infinity, you don't see this, you don't see this. So what you would see, you would kind of, you have this okay, and this is now a simple curve. And what was established, they would establish the duality. That if you define kappa, let's say kappa star, which is 16 over kappa, then for any kappa is larger than 4, you would have this kappa star, which would correspond to a simple curve, and it's a hull of this curve. And again, I can go like 4 hours discussing all this kind of beautiful mathematics. And now the question is, does it have any relation to turbulence? And I have an older friend who actually forced me to learn all this. And I hate learning new mathematics, so I really kind of hated all this. But you'll do something with it. And then I started to kind of fantasize, would it be possible that some lines in turbulence would belong to this class? Okay? And so what's your first natural assumption?
Can I ask a quick question
Yes.
before we move on? Is there any way to understand that 16? Like a simple way to understand it, or is there something we haven't?
Good question. First of all, 8 is an end of story. Namely, that if there is a fractal dimension of this curve, which, if I'm not mistaken, that df is 1 plus 8 over kappa, something like this. So when kappa hits to 8, then you feel the plane. Okay, so it's already true. So in a sense, this 16 is just because it's 4 is so special, right? So you start from almost straight line, you increase kappa, you're getting, curvier and curvier. And then when you hit 4, you start returning to itself, but then you had a dual, which does not return. Well, I wish I would have more mathematical intuition about it. But 8 is the end of story here. So in a sense, when kappa is 8, then this is 2. Good. So now what is you can do here, again, in terms of parentheses, you can look of most interesting natural scalar field that you have in 2D, and its vorticity. Okay, so again, vorticity is a pseudoscalar. You can also introduce stream function so that omega could be written as Laplace of psi. Psi is called stream function, namely that Vx is d psi dy, and Vy is minus d psi dx. And I'll return to it in a more general setting. So what can we say about omega if it is indeed such a field like this H, for which I am, so first of all, you remember that we have this scaling delta V cube scales like R. So if you're asking how omega at the scales R scales, you can say that this is the delta V divided by R, so it's R minus 2/3, right? Which means that if you say that your omega R, okay, omega 1, omega 2, you would expect to scale as R12 minus 4/3. And that's too slow by this criteria, namely, it would tell you that you don't expect percolation because your correlation decay too slow. But on the other hand, omega is not a Gaussian field. We know that we have a certain moment of velocity, and you can actually recompute, which we did with Zamolodchikov, and it was actually not a computation, but kind of plausible hypothesis. So omega is not a Gaussian field. It has certain moment because time reversal is broken, but still you may try. And so essentially I had some kind of wild ideas what it could be. So what you take this omega and you look at the line in turbulence. So you have this kind of big, I wish I'll show you, I put it in the lecture notes. You just look at the line omega equal to 0. From the viewpoint of geophysics, it's a very important line. It's where it rains in our atmosphere. So when you look at the atmosphere, you have omega, how you define sign of vorticity? It's arbitrary, but you can say there is a direction of my planet rotation. So I just call positive and it's called anticyclone. Where my omega is positive and where my omega is negative is called cyclone. Why it's important for meteorologists and for us living on this planet. So if you have an anticyclone and it kind of rotates the same way as the planet rotates, it's locally has a higher pressure. You know, atmosphere is just why it's almost two-dimensional. It's a very thin layer, this 10 kilometers, and the scale here like 500 kilometers for anything which is kind of weather determinant. So this would be anticyclone, and this would be cyclone. So this is the low pressure region, and this is high pressure region. And the zero line corresponds to the boundary. And that when your low pressure, your high pressure changes into low, it's usually where it rains. It's usually, so it's kind of important, right? And we have, when you see this meteorologists give you, weather forecast, it usually shows this large scale, typically scales of from 100 to 1,000 kilometer scales, where it shows these big vortices. So what we did, we look at this line. And well, it's a very complicated thing, and of course we not took it from meteorological data, we just took supercomputer, run two-dimensional Euler equations driven by small-scale forcing, run it like for 2 months, and obtain a big, 10,000 by 10,000 box filled by a lot of different fractal curves. And what we found is SLE kappa equal to 6, which means exactly like in percolation. We found this fractal dimension and all the bells and whistles. Technically, it's now pretty easy because now it's very popular. You can look, there are many fractal curves in nature, and people did in the last, I don't know, maybe 10, 15 years, just run every such set of curves. It's ran statistical through this, relatively simple algorithm. So you have your curves, whatever it is. You just arbitrarily cut it, you call it half plane, then you break this into pieces of straight lines, and you just do your conformal transform exactly like it's done over here. Namely, you absorb this curve into your boundary step by step. It would give you this psi of t, namely the driving function, the image of the tip as it moves on your image, and then it's a pretty standard algorithm which you check that it's a Brownian walk. And the moment you check that it's Brownian walk, it gives you count. That's how it works. What was the most interesting thing? First of all, we know that our scaling is too slow to give percolation. So would it be a Gaussian field, then it would not be percolation. So we checked it. So what we did, we took our vorticity field, the bulk field, vorticity field, and scrambled the phases. Namely, we killed all the high accumulants of this field, preserving the same pair correlation function, which behaves like this. And this SLE property immediately disappeared, which is kind of very, very mysterious. John Carney was a referee, and he actually kind of forced us to do this. This was a very good idea. The first draft, he looked and said, guys, try to show that it's called Harris criterion. So we scramble the phases and this property disappears. So it's something very strange. It tells you that there is kind of your pair correlation decays too slow, but there are some high accumulants which essentially make your line behave as if it is an isolated line of a short correlated field. Okay? And That was very mysterious. At this point, nobody ever were able to tell where in the earlier equation let me write it as following, psi omega, where psi and omega are related by this relation. Where here it's written that kappa equal to 6. Okay? And then, as usually you do in physics, if you cannot understand a given system, you try to look at it as a part of a family. So you find a parameter which you can change and see how everything else changes. And that's the last thing which I'll tell you today. So now what you can do, you can consider a generalized hydrodynamics, which is kind of a set of real systems. So generally, you can consider a scalar, let's call it A, okay? So you can consider a system which satisfies the following equation. This is the Poisson bracket, which means d psi dx dA dy minus d psi dy dA dx, which is the same as dA dt plus v graph A. It's just a transport equation. But the relation between A and psi could now be arbitrary. So you'll say that if you write it in a, let's say, in Fourier representation, that AK is k to the power m psi k. So if the, or you can say that A is kind of a gradient to power m times psi. If that would be vorticity, that would be k squared stream function. Okay? But generally, there are different physical systems. And the most interesting for geophysicists is the system, believe it or not, is m equal to 1, which is called surface quasi-geostrophic model. And this is actually temperature. So it's temperature which produces convection on large scale, but it doesn't matter. It's a well-defined hydrodynamics, if you wish. Again, you can show that for this system, you have, again, V, which always defined, by, where is B? So your V always defines your psi in this way, and you can always show that for this system, you always have an integral of motion, which is V squared dr, but you also have A squared, because this is an equation for which any function of A is conserved. So in particular, you have A. Now, the difference is that the relation between V and A is generally different. For earlier equations, this is A is just curl of V, but generally it could be different. In particular, there is N could be even negative. This is called Charny-Obuchov-Hasegawa-Nima equation, and it describes very magnetized plasma in a very strong magnetic field, or very strong or very fast rotating layer of a fluid. So there is a kind of a whole family of such things. And again, because in all this family, you have two quadratic invariants, then you have two cascades, exactly like in the earlier equation. The properties of them are very different because when you change this n, this your kind of locality very much changes. So instead of omega being Laplacian of psi, you would have and here it was just opposite. But the answer was really interesting that you get SLE for every such model that we bothered to check. And which means that when you write this family of fluid mechanics, somewhere this M encodes, it's something which the strangest graph I ever plotted. So if you plot kappa as a function of M, that's my earlier equation, that's my 6. This is a point. Then when you come to 1, let me call it 4, but this is not a straight line. There is a point here at 3/2, which is actually lower. Okay. And then it fixed. There is such curve. And that's true mystery. And as you probably understand, you can write a respective conformal field theory for every such class. Incidentally, percolation corresponds to central charge equal to 0. It's kind of simplest universality class, right? Then here the central charge is equal to unity, so kappa equal to 4. This is like a Gaussian free field, if you wish. So there is something in this fluid mechanics which not about bulk field, but about a line, which tells that this line is conformally invariant and belongs to some well-defined class. And that's a real mystery. And I gave up. I mean, I spent 3 years trying to relate this M to this kappa, and it's something which needs some kind of new profound ideas. But for now, I mean, our initial kind of data was like 5% accuracy. It's now very high accuracy, and people checked and rechecked it many times, and this nobody knows where this miracle comes from. Okay, so let me finish with this strange thing.
What about M greater than 2?
Huh?
M greater than 2.
M greater than 2. I don't know any physical example, but I don't also know a simple argument of why it's impossible. Yeah, there probably would be something extremely non-smooth. Yeah, I guess that. So the answer is I don't know general argument, but I don't know any single physical example. For every such M up to -2, -2 it goes like this. -2, 2, there are physics all inside. But also notice that here it's independent on M. All this give isolines that belong to the same class. And here they change. Between 1 and 2, they change.
Another question. So
Yeah.
you just mentioned briefly that Falkovich conjecture is conformal invariance. So this is evidence of conformal invariance. Is there more evidence? Like, is it
No.
really this
He actually, Falkovich hypothesized that the bulk field, that the omega would be conformally invariant. Now, he spends a lot of time. I just don't want to go into something
So
which
what by bulk field? Is there-
bulk field means that omega, that correlation function of omega would be conformally invariant.
Okay.
Now you know scaling, so you can say, okay, there are these minimal models, and of course you can. And there were people who kind of, say, okay, this is this minimal, this is that. And then we spent many years with the Maluchkov, and we shown it, to much unhappiness of Polyakov, that the third moment of omega, which is non-zero, makes it impossible that the omega is a prime. That's sure. We never published it, negative thing. So we can guarantee that omega as a field is not a primary of any conformal field theory. Okay? What we found is a sector in this turbulence, which is a line, well, a set of lines, okay, which correspond to omega equal to 0. This is conformal. It's something, I initially thought that omega equal to 0, imagine that you have a region with omega equal to 0. It's a potential fluid. Yes, it's in source 3. Potential flow of incompressible fluid is just a solution, it's just, it's totally completely determined by boundary. So I saw that what remains from this simplicity is this line omega equal to 0, which carries this kind of peculiar properties. But for this thing, it's not that simple, because here there is no such simple interpretation of, because there is a whole class. Okay? So, but the bulk field is not conformal environment. He spent a lot of time trying to invent some kind of a logarithmic type conformal field series that would give, but no. The third moment kills it all. But line isn't one. So now I feel like I put this burden from my shoulders into yours. Okay, good. So any questions?
I wanted to ask about other possible generalizations. So you've done one generalization here. I can imagine perturbing very slightly off of this class. Is that something that is it a stable thing to do? Or what happens if I try to go very slightly off of this class?
Well, first of all, what we did, all this was checking what inverse cascade. We can look at a direct cascade, for example, which incidentally, we were saying that they are logarithmic for m equal to 2, but for m not equal to 2, they're not logarithmic. They also have power law. No SLE whatsoever. This is really the curves which has a kind of, they're fractal curves, but they are not conformally invariant. They aren't even scale invariant. This is a peculiar property of inverse cascade. And I'm pretty sure that if you add here any small term which is not of this nature, even preserving in incompressibility, that would destroy it.
So you don't think there's a way to do something like conformal perturbation theory here?
I would love to perturbation theory, but for this I need a trivial place to start. Right? In a sense, yeah, that would be maybe if I would go to m to infinity, but like you asked, I've never seen anything m beyond 2. I must think about it. M0 is a very non-trivial. This is actually a logarithm here. It's a non-trivial limit, but kappa just does not want this go through.
So these equations, what symmetries do they have actually?
They are of a very similar type. They are all these Arnold type systems which have quadratic invariance. And
I mean, like, okay, so we're talking about conformal invariance, it's very, which is.
you're talking about lines or about hydrodynamics?
Yeah, well, conformal invariance is something which is not obvious how to emerge, right?
Totally not.
So how about scale invariance? Do we have that?
No, I can't prove scale invariance even, not for Euler, not for any model like this. Actually, all these models are something which Arnold introduced long ago. They are like Euler equation. You know, if you take a solid body and consider its rotation, it's called also Euler equation. So what is Euler equation for incompressible fluid? It's just infinite dimensional generalization of Euler equation for the rotation of a body. What all this M corresponds is a different relation between tensor of inertia, if you wish. So they all are Euler equations. They all are rotation, and they all have the same set of symmetries, which is kind of Euler equation. Okay? They're just kind of different relation between, they're all motion on geodesics, right? Because that's what you saw about the rotation fluid moves on geodesics, right? Just a surface, how your kinetic energy and your in terms of inertia related is given by this parameter. So mathematically, they are kind of they are from the same class. Yeah, they have the same symmetries. They're all geodesic on some Lie group, right? But how I don't know. This is something. It could be that someday it would be kind of say this is just trivial, but at the moment I just don't know where in this equation encoded this stuff. Where it's written. Okay, so let me finish at this point. So we'll have a last lecture next week, and then I will give a little kind of summary and formulate more clearly several problems and describe also one problem about inverse cascade, which is different from this. Okay. Thanks for your patience. This was not easy, I guess.